Hey, glad you're here. Today we're tackling something that quietly kills more AI projects than any technical failure: cost. Specifically, we're going to talk about why your agent's context window is both your most powerful asset and your biggest expense. And I'm going to show you how teams are cutting their AI bills by 80% or more without sacrificing quality. This is Skill 5 in our 9 Essential Skills series: Context, Economics, and Optimization. If you've ever looked at a cloud bill and wondered how a chatbot costs more than your engineering team, this one's for you. Picture this: a customer service chatbot handling 10,000 conversations every single day. Each conversation averages 20 turns. Customer asks a question, the agent responds, the customer follows up, and so on. The engineering team built it the obvious way. They send the entire conversation history with every request, so the agent has full context. By context, I mean everything the model needs to see to do its job: system instructions, retrieve knowledge, conversation history, and intermediate state. It works beautifully. The agent never forgets what was said earlier. Customer satisfaction scores are excellent. Then the invoice arrives: $5,000 per day. That's over $1.8 million per year just for the customer service chatbot. The CFO calls an emergency meeting. The team does the math. At 20 turns per conversation, with thousands of tokens per turn, they're sending on the order of tens of thousands of tokens per conversation. Multiply that by 10,000 conversations per day, and you're suddenly processing hundreds of millions of tokens every single day. Nothing is broken. The system is doing exactly what it was designed to do. And that's the problem. Here's what the optimized version looks like. Same chatbot, same user-visible quality. With prefix caching, the system prompt and retrieve knowledge are computed once and reused. With sliding window summarization, only the most recent turns are sent in full, while older turns are compressed into summaries. The new invoice: $800 per day. That's an 84% cost reduction. $1.5 million in annual savings. Same agent, same outcomes for users, radically different economics. This is Skill 5 in the framework of 9 essential skills: context, economics, and optimization. Context is the most valuable and the most expensive resource in agentic AI systems. Every token you send consumes computation, increases latency, and costs real money. The AI strategist of 2026 must become a context economist, someone who understands caching, compression, and reuse well enough to make AI systems financially viable at scale. Whoever controls context economics controls whether an AI initiative scales or gets shut down. To understand prefix caching, you need to understand how large language models actually process prompts. When you send a request to Claude, GPT, or Gemini, the model doesn't just read your text. It computes mathematical representations called key and value matrices for every token. These capture relationships between words and concepts and are stored in what's called the KV cache. Computing these matrices is the most expensive part of inference. You can think of it like compiling code. The first compile is expensive, but reusing compiled artifacts is cheap. Here's the key insight: if two requests share the same beginning, the same prefix, the KV cache computation for that prefix is identical. Prefix caching means storing that computed state and reusing it for subsequent requests. When a new request arrives with the same system prompt and the same retrieved context, the model loads the cache state and only computes what's new. Time to first token drops dramatically. Cost drops proportionally. The magic happens in prompt structure. To maximize cache hits, place static, expensive content at the beginning and dynamic variable content at the end. Your prompt should flow like this: system prompt first. This rarely changes. Then retrieve knowledge, documents that stay constant across many queries. Then conversation history, which evolves predictably. Finally, the user's current query, which is unique every time. This structure maximizes prefix reuse and minimizes redundant computation. Different providers implement prefix caching differently, and these differences matter. Anthropic offers prompt caching with up to a 90% cost reduction for cached tokens, using a minimum prefix length and a short time to live. OpenAI provides automatic caching with partial savings. Google's Gemini allows explicit cache creation for very large contexts, with separate storage costs. A real optimization strategy accounts for these platform-specific characteristics, instead of assuming one-size-fits-all behavior. Standard cache eviction uses least recently used, or LRU. That sounds reasonable, but it fails for agents. Agents don't access context linearly. They loop back to earlier instructions. They revisit system prompts mid-workflow. They follow predictable execution patterns that LRU completely ignores. Research into workflow-aware approaches like KV-flow shows that analyzing the agent's workflow graph allows you to predict which cache states will be needed next. Keeping relevant context warm reduces cache misses by 30 to 50%. This matters because agents behave like workflows, not like users. Caching solves part of the problem, but long-running agents introduce a new challenge. Context grows without bound. A customer support session might span dozens of turns. A research assistant might accumulate hundreds of interactions over days. Even with caching, sending massive histories eventually becomes expensive and eventually impossible due to token limits. Hierarchical summarization solves this. Instead of keeping full history forever, the system generates summaries at multiple levels. Per-turn summaries capture each exchange in a sentence or two. Per-session summaries distill an entire conversation into a paragraph. Per-user summaries preserve long-term patterns and preferences across interactions. The system dynamically selects the appropriate level of detail based on the task at hand. The sliding window pattern combines precision and efficiency. Keep full, detailed context for recent turns, where accuracy matters most. Summarize everything older. The prompt becomes a compressed summary of earlier history, full detail for recent turns, and the current query. Recent context stays crisp. Older context is preserved but compact. Total token usage remains bounded. Semantic compression goes beyond simple summarization. It removes redundancy while preserving decision-relevant information. Entity extraction pulls out names, identifiers, and facts. Co-reference resolution replaces repeated descriptions with compact references. Information theoretic techniques prune low-value filler while preserving high-value signals. Good compression isn't about making text shorter. It's about preserving what actually matters for decisions. Here's how this works in practice. A customer contacts support about an order issue. Over 20 turns, the problem is explained, investigated, and resolved. Without compression, that entire transcript gets sent again and again. With hierarchical summarization, the full exchange becomes a 3-sentence summary, capturing the order number, issue type, and resolution. Future interactions include this compact summary instead of raw history. Same context quality, a fraction of the cost. So far, we've optimized context, but there's an even more powerful lever: caching reasoning itself. When an agent books a flight, it follows a plan. Gather requirements, search options, compare results, select, confirm. Booking a hotel follows nearly the same structure with different variables. Agentic plan caching stores these abstract reasoning templates and reuses them. Here's how it works. When an agent completes a task successfully, the system extracts the abstract plan, the sequence of steps, control flow, and decision points. That plan is stored with metadata describing when it applies. For new requests, the system searches for similar plans. If a match exists, it adapts the cached plan instead of generating one from scratch. Plan similarity detection is the hard part. The system must decide when a request is similar enough to reuse a plan. This requires embedding plans based on their structure, defining similarity thresholds, and building efficient retrieval. Done well, routine tasks become faster and cheaper. Done poorly, the system applies the wrong plan to the wrong situation. Plan caching works best for routine, high-volume workflows, not novel or high-stakes reasoning. Dynamic plan adaptation bridges templates and real-world specifics. Cached plans contain placeholders. Adaptation fills in actual values and validates that the plan still makes sense. If conditions change, say the user requests private air travel instead of commercial flights, the system must recognize when to adapt and when to generate a fresh plan. Knowing that boundary is critical. The benefits are substantial. 40 to 60% reductions in latency and cost for routine tasks. Improved consistency. Predictable behavior. When the same abstract plan executes repeatedly, users get reliable outcomes instead of randomness. Combined with prefix caching and context compaction, plan caching turns prototypes into production systems. Let's return to our customer service example. 10,000 conversations per day, $5,000 per day in a naive implementation. With prefix caching, sliding window summarization, and platform-aware prompt structure, $800 per day, 84% reduction, $1.5 million saved annually. The optimization paid for itself in the first week. Now consider a code assistant. Developers query a 50,000 token code base repeatedly. Naively, each request recomputes the entire context. With context caching, that code base is processed once and reused. Cache hit rates exceed 90%. Cost drops by an order of magnitude. Time to first token drops from seconds to under 1 second. Developers move faster. Costs collapse. One more scenario. Workflow automation. A company processes 1,000 similar travel bookings per day. Naively, the agent reasons from scratch each time. With agentic plan caching, the abstract booking plan is reused and adapted. Costs drop by more than half. Latency is cut dramatically. Employees get faster confirmations without sacrificing quality. Here's your implementation checklist. First, audit your context usage. Measure tokens per request. Identify patterns. Second, restructure prompts so static content comes first. Third, implement platform-specific caching. Fourth, add hierarchical summarization for long-running sessions. Fifth, evaluate plan caching for repetitive workflows. Sixth, monitor everything: cache hit rates, cost per request, optimization ROI. You don't need all of this on day one, but you do need a roadmap. Common pitfalls to avoid: ignoring caching entirely, poor prompt structure that destroys cache reuse, over-aggressive compression that loses critical information, blindly using LRU eviction, failing to track costs, optimizing before understanding usage, and ignoring platform differences. You can't optimize what you don't measure. Looking ahead, context economics is evolving quickly. Learned compression models discover optimal summaries automatically. Predictive caching preloads context before it's requested. Semantic caching reuses computation based on meaning, not exact wording. The direction is clear: more reuse, less waste. Here's the bottom line. Context economics is what makes production agentic AI financially viable. Every token costs time and money. Without optimization, costs spiral. With prefix caching, hierarchical summarization, and plan reuse, teams routinely achieve 50 to 90% cost reductions while maintaining or improving quality. The most successful AI systems of 2026 won't just be the smartest. They'll be the most economically efficient. This is Skill 5, Context Economics and Optimization. Master caching theory. Understand compression deeply. Apply economic thinking to every token decision. These are transferable principles that outlast any specific model or framework. If this deep dive was valuable, consider subscribing and joining our growing community of Agentic AI strategists. We publish in-depth, practical content focused on building systems that actually work in the real world. And if this resonated, drop a like. Engagement helps this kind of content reach more builders wrestling with real AI costs and real production challenges. Enable notifications so you don't miss the next deep dive. The agentic AI landscape moves fast, and we're building a complete education, one skill at a time. Context is expensive, but ignorance about context economics is far more expensive. Audit your token usage. Restructure your prompts. Implement caching. Track your costs. The savings will fund your next innovation. All right, that's context economics. Let me leave you with this. Every conversation about AI cost eventually becomes a conversation about context. How much are you sending? How often? Are you recomputing things you've already computed? The teams that figure this out early don't just save money. They buy themselves room to experiment, to scale, and to take risks that their competitors can't afford. So here's my challenge. Pick one technique from today, just one. Audit your token usage. Restructure a prompt. Enable caching. Measure the difference. Start small, prove the value, then expand. Thanks for spending this time with me. If you found this useful, you know what to do. Subscribe, drop a like, ring that notification bell, and I'll see you in the next one. Until then, keep building, keep optimizing, and keep pushing what's possible.